Section 5.3, Properties of Metric Spaces. Definition 5.14, let XD be a metric space. For sets A and B in X, define the distance between A and B by the greatest lower bound of the distances between points in the sets A and B. And this greatest lower bound always exists because this set of real numbers, the set of distances, is bounded below by, for example, 0. And if a set of real numbers is bounded below, then it has a greatest lower bound by the axiom of completeness. Okay, so let exercise 5.23, let XD be a metric space. Let A and B be disjoint subsets of X that are closed in the topology induced by the metric D. Prove that there exist disjoint open sets U and V such that U contains A and V contains B. You might notice that this is a sort of generalization of the Hausdorff property, because in a metric space, single point sets are always closed, and the Hausdorff property says that given a pair of distinct points, we can sort of surround them by disjoint open sets, and this exercise is generalizing that to sort of any pair of disjoint closed subsets, not just pairs of distinct points. All right. Well, when I saw this problem, the first sort of strategy that occurred to me was maybe the distance between these two sets A and B, if they're disjoint and closed, is going to have to be positive. And well, then I could just sort of let U and V be all the points within distance from A to B over 2 of A and B. And then hopefully those U and V wouldn't overlap at all. Okay, so then you could define that more precisely by letting U be the union of a ball around every point A in A with this radius, distance from A to B over 2. And similarly, V will be balls around every point in B with that same radius. Now, the trouble with this line of attack is that even when A and B are closed and disjoint, you can still have the distance between the sets being 0. And here's an example of how that could happen. Maybe A could be just the horizontal axis in the plane, and B could be your favorite hyperbola. And well, as you go far off to the right here or far to the left, you get sort of pairs of points in these two sets which are closer and closer to one another. In fact, there's a pair of points whose distance is any positive real number that you want. And so the greatest lower bound of all those distances is 0. Okay, so the distance between the red set and the blue set would be 0 here. And then we're in trouble, right? Because these balls we're defining up here would all have radius 0. So it'd be empty. They wouldn't even contain A, and that's not allowed. So, okay, so that doesn't quite work, but it's not too far off from the right idea. Instead of looking at the distance between the two sets, what we want to do is look at the distance from a point in one of the sets to the other set. Okay. So sort of go one point at a time. All right. So if you do that, say you take a point A and A, it turns out that the distance from that singleton set to the set B does have to be positive. So let's prove that by contradiction. Assume for contradiction that actually the distance is 0. Okay. Well, if we can prove from that A is a limit point of B, then since B is closed, A will be an element of B, but it's also in A, right? So it'd be in both, which is a contradiction since we're assuming that these sets A and B are disjoint. All right, so how can we prove that A is a limit point of B? Well, we're supposed to take any neighborhood of A. Right, so given any neighborhood, we'll call it W, of this point A. Well, we have a basis of open balls, right? That's the basis for this metric topology. And so by sort of the local criterion for openness, we know that there exists some b sub d centered at a of radius some epsilon, which is contained in that neighborhood w, excuse me, which is depicted in this diagram here. All right, well, I claim that by the definition of greatest lower bound, there exists some element b in the set B whose distance from A is less than epsilon. Right. So B is in B and its distance is less than epsilon. And that's going to imply that B is an element of this ball about A of radius epsilon, okay, which itself is contained in W. Okay, why does this B have to exist? Well, if it didn't, then epsilon itself would be a lower bound on all of the distances from A to points in B, right? But epsilon's positive, and if that's a lower bound, then 0 is not the greatest lower bound, right? There's one that's greater, and so that can't be. So epsilon's not a lower bound of these distances, therefore there exists one that's smaller than epsilon. All right. So we've found a B in the set B, which is contained in this ball of radius epsilon, which itself is contained in W. Okay, well, we found a point in this neighborhood W of A, which is also in B. Okay, so we've shown that every neighborhood of A intersects B. Let's write that down. We've shown that every neighborhood of A intersects the set B in some point other than A. So that's what it means for A to be a limit point of the set B. Good. Next, bring this up here. So, okay, so what did we show? That we showed that the distance from the single point set A to set B is positive. So if you sort of just flip the argument around, you can show that for every B and B, the distance from the set A to the single point set B is also positive. And okay, so for each A and B, let's define these epsilons to just be the appropriate distances from that point, in this case from the point A to the set B, and I'm going to divide by 2, okay? And same thing here, the distance from the set A to the point, to the single point set B, divided by 2. And then I'm going to define my open sets U and V by just taking, for U, the union of all of these little balls about the points in A, and for V, the union of all these little balls about the points in B. Okay. And we just need to check that these U and V contain A and B and are disjoint, right? They're certainly open because they're just the union of open balls, so union of basis elements. All right, so U contains A because, well, each point A in A is contained in its own ball here, right? So every point in A actually occurs as the center of one of these balls that we're unioning. And similarly for B, okay? B is a subset of V. So it just remains to show that U and V are disjoint. All right. So let's do it by contradiction again. Suppose for contradiction that we have a point X which is in both U and V. Well then, that X is, since it's in the union of all of these open balls, it's in one of them, right? It's in the ball about A of radius epsilon sub A for some A and A. And since it's in V, it's in one of these balls about B of radius epsilon B. Okay. And here comes our contradiction. So the distance from A to B by the triangle inequality is less than or equal to the distance from A to this point x that we have plus the distance from x to b. Okay, and that is, well, the distance from a to x by this inclusion here is less than epsilon sub a, and by this one, the distance from x to b is less than epsilon sub b. And we have chosen those epsilons to be half of these distances, and so I suppose I should actually put an equal sign right there, because the epsilon, sum of the epsilons is equal to the sum of these distances over 2. Okay, and then, well, this distance here is the greatest lower bound of everything of this form, distance from a to b, where b is an element in the set B. Okay, so this is a lower bound of things like this, which means that this is certainly greater than or equal to the lower bound. And similarly for the distance from B to A right here, I'm not quite sure why I have those in the other order. Let's just flip that around. Okay, and then you add half of it up twice and you get distance from A to B. And the contradiction is that if you string these together, you get the distance from A to B is less than itself. All right, which can't be the case. So we've shown that U and V are disjoint. In terms of the picture up here, you see this little epsilon ball about A here is, well, the epsilon sub A, you want to look for the point in B that's closest to A, which would be this point B down here, and so this epsilon sub A should be sort of half of this distance. And then if you look at B, the closest point in the set A is about up here, so epsilon sub B would be half that distance. And the contradiction comes by, well, if X is in U intersect B, it has to be in sort of two such balls, right, about a point A and a point B. And so what we end up doing is measuring the distance from A to B by going from A to X, and then from X to B. And well, you just can't get that far. You can't get all the way from A to B by doing that, basically because X couldn't be in two of these epsilon balls at the same time. Okay, you can have all these epsilon balls covering up A to give you the set U, all these epsilon balls covering up B to give you the set V, and those two open sets aren't going to overlap at all. So that's how it works.